Hello teammates, it's Mr. Nannini. I'm going to take you through the solutions for the Christmas practice problems. And I had a high-speed microphone that I was looking for about 2 days, which is why this is late and I just gave up. And we'll talk about this in class, but this takes you through the structure of the final exam and what the prudent student will do to be prepared. What you don't want to do is wait till the Wednesday before the exam to figure out you don't know something. It'll be very fair, but it's going to be comprehensive, which means I'm going to look for your level of mastery that you've established over this term. We got 3 units: 2D motion, and I'll post these standards as well. Circular motion, universal gravitation, and the one we just completed. Conservation of energy. And I just gave a couple, and again, I'm very cautious because some students are brought up in the habit of reviews, and the review is really just kind of a practice test, and the actual test is really just the review again. I don't believe in that at all, and you understand that about me. I'm looking for what you really learned, not what you can just repeat a pattern on. So I gave you a couple free fall ones. I'll walk you through real quick. If you have questions, please come see me. So you've got, people used to, I don't know if it's done much anymore. They did them in circuses. They launched people out of a cannon. They'd have compressed air in the cannon. Someone get in, they'd launch them. So in this case, he's Murray the Magnificent. I just made that up. He's launched out. His initial velocity is 22 meters a second. And recall that you go into free fall the instant the only force acting use gravity. So as soon as he leaves that, and we want to figure out how high his change in y. And so given the initial velocity, when he gets to the highest point, his velocity in the y is 0. We're going to use acceleration for gravity of 10 meters second. We're going to use the third kinematic equation with your final velocity being 0. You can always solve. You can put in your variables first, or you can just use the numbers. I used the numbers this time. You're gonna square 22 meters per second, get 484 meters, 484 meters squared second squared, divided by 2 times 10, and you're gonna get a height of 24.2 meters, a max height. It's good. His velocity after 2 seconds, and so if he got to the highest point at 2 seconds, it would be 0, but we don't know that. So we're going to use the first kinematic equation because we've got his final velocity, his initial velocity, acceleration, and the time. So we're going to solve for that final velocity at 2 seconds, and we're going to get 2 meters per second. Good. Number 2. Divers running. He dives horizontally. Again, in this unit, you had free fall, which is just an object falling straight down. You had a horizontal launch angle, which is an object initially moving horizontally. And you had a general launch angle, which was an object moving not horizontally. We're going to determine the height of the cliff. We're given 4 meters per second, dives horizontally from the edge of the cliff, hits the water 3 seconds below. How high was the cliff? So it's essentially a free fall problem here. Use the second kinematic equation. Initial velocity in the y is 0. Recall your xy chart. Fill that out as much as you can. Final velocity, initial velocity. Oh, I missed that. Change in y is what we want to find. And we use that second kinematic equation, solve for that. We should get 45 meters. How far from the base of the cliff did he hit the water? So recall in projectile motion, 2D motion, your velocity in the x is constant, and so it becomes a constant velocity problem. Change in x over change in time. You're going to solve for change in x. Velocity initial times time. You're given the initial velocity. You're given the time. He goes or she goes 12 meters. It's good. Softball player wants to determine her pitching speed. She throws the ball directly horizontally So that's your key word. If it's horizontal, you know it's horizontal launch angle. No tricks. She's 4 meters above the ground. She sees the ball hit 25 meters away. For any kind of 2D motion problem, you're usually going to have to determine the time. And so what we're going to do here, we're given the change in y. We've got our xy chart. We're going to rearrange to solve for time, and we get a time of 0.89 seconds. Determine the speed she threw the ball, and again that horizontal velocity stays constant. So if it went 25 meters and it went 25 meters in 0.89 seconds, her velocity was 27.95 meters per second. Recall that anytime you can draw a picture, it works to your advantage. Next section is uniform circular motion, universal grav. We're given a situation, we got a roller coaster cart at 2 points in a track. We're given the radius of the track, the cart speed at that time, how heavy would a 60 kilogram passenger feel at point A. So I selected this one to get back to that normal force is your apparent weight, how heavy you feel. So we want, so that how heavy you feel ties directly to your normal force. Right, it's the force pushing back up on you. That's what you feel as your weight. The force, the earth pushing back up on you. So you're going to solve the centripetal force equation. You're going to get a centripetal force of 18 newtons. It's not very high because the radius is fairly big. The velocity is pretty small. And so we know that our net force has to be down because this would be the center of our circle. And so we got to have more down force than up force by 18 newtons. The only force down is the weight of the person. And so that can't change. So we got to take 16 newtons off the up force. So that's our free body diagram. Recall that quantitative means with numbers. Force, normal, force, gravity. We're not going to do on-by statements for the final exam. They serve their purpose. All right. At point B, we're given the radius of the track. We want the rider to feel 4 times as heavy now, so 4 times her weight, so 2,400 newtons. How fast are they traveling? So we know if we want to be 4 times her weight, so her weight is 600 newtons. 4 times her weight is 2,400 newtons. We're gonna use our centripetal force equation, and we're gonna solve for a force of 2,400 newtons because that up force is towards the center of that circle. 2,400 newtons. We're gonna rearrange this to solve for velocity. So centripetal force times the radius divided by the mass. Square root that. We get 22.8 meters per second. It's good. Little universal gravitation. We're given space shuttle's all retired now, but this is still a good problem. I guess I could do the International Space Station, but I like the space shuttle. It's been a minute since we've had a shuttle. Given the mass of the shuttle, mass of the Earth. For this problem, 5.98 is the mass, but this is whatever. Unless I make a tragic mistake, sometimes I'll change the numbers just to have us think a little bit. We're given the height of the shuttle above the Earth, the radius of the Earth, the tangential velocity of the shuttle. So recall that the universal gravitation equation works if you have you need the total distance from the center of that planetary body to where your object's orbiting. So you're going to add the radius of the Earth and the height the shuttle is above the Earth. You're going to get so in this case, force centripetal equals your force gravity. And so you're given the mass of the wait a minute. I forgot to use my G there. No, I didn't. No, I didn't. I'm sorry. I don't know what I was doing. We can get this force. We know centripetal force equals force centripetal. I'm watching my time because YouTube times me out after 15 minutes. Mass of the shuttle. It's always the object in motion that you want the mass for. So Earth's mass doesn't affect us for the centripetal force. We want the space shuttle. It's velocity squared. That whole radius, that whole distance. So the radius of the Earth plus the height is above the Earth, and you get 8.71 times 10 to the 5th newtons. Then I ask you to solve the same thing using universal gravitation. Fg equals g m1 m2 over r. You're going to put your values in. You want this. Again, here I had them both separate so you can see what I did. Here I added them both together, right? And you're going to get 8.55 times 10 to the 5th, which is pretty much the same thing. Some rounding error. If it would have been different if I used the actual radius of the Earth, but that's okay. If I ask you to solve a problem like this, if somewhere in the future someone asks you to solve a problem like this, and you're pretty darn close, you're good. You're good. Don't fret. If you don't get exactly 8.71 or 8.55, you're good. It's good? All right, let's see. Let me do a time check. All right, 4 minutes. 4 minutes left. Conservation of energy, little roller coaster. It should be pretty fresh, but it's worth going back through. Got a mass of a roller coaster, begins at position 1 with the velocity. We want to find its velocity position 2. It loses 10,000 joules of energy due to friction, so energy non-conservative. Determines its velocity position 2. And we're going to create a quantitative energy bar graph again, so with numbers. So energy initial equals energy final. Initial energy, because it's in motion, we've got kinetic energy and gravitational potential energy. Easy money here is lowest point is 2, so we're going to use that as our 0. And this, so after we're going to have kinetic final plus that energy we lost to friction. We're going to put our symbols in. We're going to put our values in. We're going to solve for velocity, and we should get 27.01 meters per second. Or 27 is fine. Don't get wrapped up on the decimals. And then we can calculate that as about 729,000 joules. Right, so we put that value back in, 1/2 mass velocity squared. We would get that. So initially, based on the height of 32 meters, we had a gravitational potential energy of 640,000 joules. We were moving at 10 meters per second. With that mass, we get 100,000 joules, so 640,000, 100,000. GPE, kinetic. Your system is your cart, the Earth, and the track. Because the track is taking some of the energy off, so you got to include that in your system. If there was no friction, you just have the cart and the Earth. After, so at point 2, because we picked that as our 0 point, 729,000 joules kinetic energy, and that energy we lost to friction. So they should add up to the same. Yeah, and they do within 1,000. So don't fret. It's just how we round. If you carry those decimals all the way out, you get the exact same thing. But this shows, so 640 and 100 is 740,000. So 729 plus 10 is 729,000. So essentially the same thing. It's good? All right, teammates. Ask me if you got questions. See you tomorrow.